Good afternoon. So the last two topics of this chapter is about how we represent functions as power series. So remember we talked about last time that the idea is to use a power series representation in place of a function in situations in which this is advantageous. For example, let's say you have a function that you cannot otherwise integrate, then you may want to replace it with a power series representation, and then maybe you can compute the integral or at least to approximate that integral. And these type of representations are good for many other things. Approximations in general, these are where they are useful in most of the time. And the goal, like I said in the last two lessons, is to see how we can actually have these representations for various functions. The very last topic on the chapter is about how we do this for a generic function that has certain properties like differentiability. But in today's lesson, we will see that we can obtain these representations by simply manipulating known representations that we know already they exist. And as I said before, we already have such a representation. It's the only series that in case when it's convergent that we can actually found its summation, so the limit of the sequence of partial sums. So the only series for which in the case it's convergent we actually know what it converges to, and that's the the geometric series. So the geometric series, remember, in a more general setting was like this. So a plus ar plus dot 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 ar to the n equals a over 1 minus r, as long as r is between minus 1 and 1. So what I'm going to use today is a version of this view as a function, just to keep things streamlined. This constant a can be dealt with separately, so to speak. You don't have to carry it over in the examples that I'm going to show you in this lesson. So the version of this formula with a equals 1 and r equals x, so x is basically the variable of the function. With this modification, that means we already have a power series representation for the function f of x equals 1 over 1 minus x, with x between, again, minus 1 and 1. So basically the function itself is the sum of that series. So you could view 1 over 1 minus x, you can view it as a power series in the form of 1 plus x squared, x to the n, and so on. Or in a more compact form, summation from 0 to infinity, x to the n. So we know that we can actually use the equal sign between 1 over 1 minus x and the summation from 0 to infinity for x to the n, as long as x is between minus 1 and 1. Remember, there are always restrictions on when you are allowed to use this representation. You cannot plug in any number you like, but just any number between minus 1 and 1. So the radius of convergence obviously is 1 for this power series. So it actually diverges for 1 and minus 1 at the endpoints. So here's the key part of today's lesson, and then we'll follow up with examples. You can view this as a formula, meaning that you can replace x with any expression that is still in that interval of convergence between minus 1 and 1. And in particular, if this expression is also a power of x or a constant times the power of x, that gives you basically other power series representations. So the main idea is to essentially manipulate the given function for which you want to find a representation so that you obtain something like this: 1 over 1 minus some expression, right? Some expression. I'm going to basically emphasize this expression by a little square because it can be basically any function in x. And then you're allowed to use the formula. You can replace this by the summation from 0 to infinity with that expression to the power n. As long as, again, this substitution you make is still between -1 and 1. So you'll have to make that condition -1 and 1. You have to establish that condition from the get-go. And I'm basically showing this in this schematic form because the actual steps in each problem vary depending on the problem. But the idea is to have 1 on the top over 1 minus some expression so that you could use the formula given by this geometric series. So let's start with something very similar to 1 over 1 minus x. So let's say, and by the way, the question here again is to find power series representation. That is the question for all problems that follow from here. So as a first example, let's say you have 1 over 1 plus x, right? So not 1 over 1 minus x. Well, I can still write this expression as 1 over 1 minus something by simply writing plus as a double negative. And then I can go to the actual formula and then just replace on the right hand side x with minus x. And voila, this is the power series representation for 1 over 1 plus x. It's customary to take out all coefficients and leave x to the power just to match the typical way we write a power series. Remember, a power series in general, so the general form of power series is summation from 0 to infinity, some coefficient that may depend on n, x minus some constant maybe to the power n. That's the most general format of a power series, centered at a. This one will be centered at 0. All of these examples will be series centered at 0. But see, this is why we take that -1 to the n, because that'll be basically your Cn. So that's the standard way to write your answer. But again, notice that all we did was just rewrite the given function so that we can match it with the formula here on the top corner. And other examples may involve more steps, right? So there are lots of other examples that are reducible to this formula. And of course, other examples cannot be used, with this formula, which is the reason why we learn a more general strategy to come up with this power series. But for this lesson, again, we stick to examples reducible to this geometric series, basically, to 1 over 1 minus x. So what if you have something else like a constant, 2 over 3 minus x? Well, as I said before, you want to leave 1 on the top, so I can move, so I'm going to move actually later 2 out, so I can view the top as 2 times 1. And because on the bottom you want to create 1 minus some quantity to match it with the formula, you want to pull out 3 between 3 and x. So you pull out 3 and you get 1 minus x over 3. Keep the constant out so that you can emphasize 1 over 1 minus whatever you obtained there, which is x minus 3 in this case. So again, just for this piece, now you can apply the series representation by replacing x with x over 3. So this is going to be 2 over 3, summation from 0 to infinity, x over 3 to the power n. You can leave this 2 over 3 out, or you can bring it inside. It's up to you. I usually bring it inside. And this is going to be 2x to the n, and then 3 times 3 to the n. And then you can combine 3 and 3 to the n as 3 to the n plus 1. So the representation for 2 over 3 minus x is then summation from 0 to infinity, 2 over 3 to the n plus 1 x to the n. Now, always write down the interval of convergence. Remember, when you replace x with x over 3, that x over 3 should be between -1 and 1. So again, take a look at the actual formula on the top corner here. 1 over 1 minus x is summation of x to the n if x is between minus 1 and 1. And that means if I replace x with x over 3, that means x over 3 should be between minus 1 and 1, which means x should be between minus 3 and 3 if you multiply by 3. So the radius of convergence for this second example is equal to 3. It just occurred to me that I forgot to mention this discussion in the first example, but here the radius of convergence ends up being the same. Here in the first example, we replace x with minus x. So minus x should be between minus 1 and 1, but if I multiply by a negative, I end up again with x between minus 1 and 1. So as it happens in the first example, the radius of convergence is still 1. But in general, it's different because it all depends on what you plug in for x. So let's stay tuned for more examples. All right, so bottom line, as a general strategy, if it's possible, of course, is to write your function, if possible, as x to a certain power of a times 1 over 1 minus maybe a constant, I don't know, k, x to another power b, where a and b are some positive integers. So if you can write your function in this configuration, then you could probably end up with a power series representation, again, using the fact that 1 over 1 minus x is summation from 0 to infinity x to the n if x is between minus 1 and 1. Because see, if you do it like that, and I'm going to show you immediately an example that leads to this, then this parenthesis is the one that can be replaced by the series representation by simply replacing x in the formula here on the left with whatever follows after 1 minus. Something like that. And then you can bring x to the a inside and you will end up with basically a power series. Cn x to a certain power that depends on n. It doesn't have to be n, it could be any, other numbers that depend on n, other natural numbers that depend on n. But, as long as you have something like this, then you could go ahead and use this power series representation. So here's an example, another example. So this will be example 3. Let's say you have x squared over x to the power 4 plus 16. So again, you want to leave 1 on the top, so I'm going to keep x squared out for a moment. And I'm going to switch the order here just to emphasize the element that is going to be 1 after I manipulate it further. So 1 over 16 plus x fourth. 16 needs to be 1, which is the reason I'm going to pull out 16 from 16 and x to the 4. So you're left with 1 plus x to the 4th over 16. And then keep x squared over 16 out for a moment. And then write the bottom as 1 minus something, which forces me to write plus as a double negative. So now you are in the proper form to use that power series representation. So you're going to write minus x fourth over 16 everywhere you see x on the right hand side of that summation. Minus x to the 4th over 16 to the power n. And don't forget, this is valid only if minus 1 is less than minus x to the 4th over 16 less than 1. We're going to have to simplify that inequality so that we have a condition on x to know when this representation is valid. We'll do that at the end. Let's manipulate this further, this series. You want to basically isolate x to the power and, extract the other constants. So minus 1 to the n on the top, and then x to the 4n divided by 16 to the power n. And now you can bring x squared over 16 inside the summation. And then combine again the powers, if any. So x squared with x to the 4n becomes x to the 4n plus 2. And then 16 to the power m plus 1 on the bottom. So this will be the representation for the function x squared over x4 plus 16. What about the radius of convergence? If I multiply by a negative, that's minus 1 less than x4 over 16 less than 1. This is always positive anyway, so I can take the right hand side only, so x4 is less than 16. If we take the fourth root on both sides, you end up with absolute value, because remember x could be negative since you have an even power. So that's going to be 2. Fourth root of 16 is 2, so that means x could be between 2 and minus 2. So the radius of convergence is 2 for this power series representation. So you can plug in any number between minus 2 and 2. Let's see, I think we have 2 more examples, because, well, one more before I talk about integration or differentiation. Because as it turns out, one can integrate or differentiate power series, and that allows us to obtain power series for a larger class of functions. So it's even more flexible than it is already. Sometimes you may have to do things you learned before with partial fractions, like long division. So here's another example that requires an extra trick under the sleeve. So let's say you have x minus 2 over x plus 1, and again you want a power series representation in the form of powers of x. So you can't do this, by the way. That's not helpful. So if you try to do something like this, to move x minus 3 out, and then replace 1 over 1 minus x with this, that's not helpful, because we want a power series centered at 0. That's the goal here. So you want just the summation of powers of x, and this x minus 3 is kind of a trouble here, right? If it was just x by itself, then you could combine it with x to the n, like we did it before, and you just had powers of x, but you don't want x minus 3 as a factor there. So how do you fix it? Well, you could do long division, and that, in this particular case, and that actually leaves a constant on the top. So let's do the long division. X over x is 1. The remainder is minus 4, and that means x minus 3 over x plus 1 is actually 1 minus remainder 4 on the top over x plus 1. So it's fine if you have essentially a power series plus a constant, because that constant can be combined with the first term in the power series, which is also a constant. So I'll show you what I'm talking about immediately. Let's finalize this. So 4 over x plus 1, again, if we pull the 4 out and we write x plus 1 as 1 minus x, for that second term, we could use now the power series representation. And now you get your power series for x minus 3 over x plus 1. You could leave it like that, although if someone is asking you what is the first term in the series, that first term includes 1 as well, because see, if I expand this, so let's write it like that. If you were to expand this, you have 1 minus, and then when n equals 0, you have 4 minus 1 to the 0, x to the 0, which is 1. Then the next one is going to be with plus 4 x, then it's going to be minus 4 x squared, and so on. So actually the first term will be minus 3. But you could leave it like that because this minus 3 doesn't belong to this summation, basically. So I mean, the pattern of the summation is, you know, 4 minus 1 to the n x to the n, and then 1 on the outside. So it's perfectly fine to leave it like that, as long as you understand that the very first term in the series, the constant term, has to include 1 as well. Make sure the sign is correct. So if n is 0, that's minus. Yeah. All right. So on the next page, we're going to talk about integration or differentiation of the power series and how that helps us to obtain power series yet for other types of functions. So stay tuned for the next page. All right. So take a moment to write this down. This is just a brief way of saying that you're allowed to differentiate or integrate a series, and then we'll see what's that good for. So the idea is, given f of x a power series centered at a, so the most general format of a power series, right? So c naught plus c1 x minus a, c2 x minus a squared, and so on. Then the derivative of f and the antiderivative of f are power series with the same radius of convergence. So this basically tells you that in this case, we can differentiate or integrate a series term by term. That's not actually automatic for a series of functions. That's actually one of the major concepts or questions in real analysis, you know, under what conditions you could pass the differentiation or the integral over each term of a series. Because remember, we still have to define what we mean by, you know, infinitely many, you know, distributing the integral to infinitely many terms, right? So that's not actually a trivial thing to ask, but we take this without proof and for granted that in the case of power series, one can actually do that. So one is allowed to do that in the confines of the same interval of convergence. So the radius of convergence is the same. Okay, so what does that mean? It means that if you have a function given as a power series, and you want to obtain a power series for its derivative, you could simply differentiate. So term by term. So that means c naught becomes 0. So the derivative of c naught is 0 plus c1 times the derivative of x minus a, which is 1. c2 times the derivative of x minus a squared, which is 2x minus a to the power 1. And then so on. The nth term would be cn n times x minus a to the power n minus 1, and so on and so forth. It's customary in this case, if you want to write it as a summation, to start the summation from 1, not from 0. So the generic term will be now n cn x minus a to the power n minus 1. Simply because when n equals 0, that term was 0 anyway. Now, it won't be a mistake if you do it from 0 to infinity, because, you know, n is a factor here, so the first term will be 0 anyway. But you will notice in many books, once you differentiate a power series with this constant term in the beginning, you have the summation starting from 1, not from 0. And then by the same token, one can do the antiderivative of a function by differentiating the series term by integrating term by term. So here we have c naught times x plus c1, the integral of x minus, I should say here, because I want to keep the pattern, let's see, we're going to write it actually, let's see, the integral of yeah, we're gonna write it as a constant. I'm gonna do a little gimmick here because I want to write it I want to write it in to follow the pattern. Let's continue to do that. I'll show what I'm talking about. So the second term, when you integrate it, is going to be c1 x minus a squared over 2. It's like a u substitution. You can replace u with x minus a, plus c2 x minus a to the power 3 over 3 dot 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 cn x minus a to the power m plus 1 over m plus 1. And then it's going to be another constant of integration. Remember, when you do an antiderivative, you have a constant of integration. To come up with the summation here and follow the same pattern, I'm going to basically add and subtract a here for x, just so that I have c naught x minus a, so that I have x minus a on all terms. And then the next one will be c1 x minus a squared over 2, cn x minus a to the power m plus 1 over m plus 1. And here when I did add minus a plus a, you have c naught times x minus a, and then you're left with c naught times a, which can be combined with this one, with the arbitrary constant, and you can just call it c again, another constant of integration. So when you do the summation, when you write the integral as a summation, you can just write the constant of integration plus the summation from 0 to infinity, cn x minus a to the n plus 1 over n plus 1. So we could have integrated inside the summation already, but I just wanted to show you term by term how this looks like. And this is for the derivative. So we're going to do the examples on the next page, but the idea is that, if you start with a function that is given in terms of a series like this, and you want to differentiate it, you don't have to expand it. You can just differentiate inside the summation, or you can start from 1 like I said above, and if you want to integrate it, then again you could do that integral inside the summation. Just don't forget to add another constant of integration outside the summation as well. So we could do that, and we maintain the same radius of convergence. Now the question is, what is it good for? Well, it's good in the sense that the function that you may want to represent as a power series could be the derivative or the integral of another function that you know. In our case, for example, maybe a function that's related to 1 over 1 minus x, to that formula that we used here. So let's look at a couple of examples. All right, so this will be my 5th example. So let's say we want to find the power series representation for 1 over 1 minus x squared. Okay, so first of all, notice that if you think about replacing 1 over 1 minus x with the summation of x to the n and then square it, that's not helpful. We can't really expand an infinite sum to the power 2. The goal is to have this function as a sum, not a sum to the power 2, not the infinite sum to the power 2. So that's not going to help. But 1 over 1 minus x, as it happens, is actually the derivative of 1 over 1 minus x. Okay, so just check yourself. If you do the derivative of 1 over 1 minus x, it's going to be just 1 over 1 minus x squared. So on the other hand, for 1 over 1 minus x, we do have a power series representation. It's summation from 0 to infinity x to the n. And all we have to do is to differentiate that, which we know we are allowed to. So this is simply equal to summation from 1 to infinity n x to the n minus 1. And you're done. And again, the radius of convergence is the same. So this converges for x between minus 1 and 1. So now, of course, if it's not going to be the derivative of this, then you have to use other tricks, right? So, or other tools. But this is the situation when this works, when the ability to differentiate a power series is helpful. And let's do a couple of more examples involving the integral. So for example, let's say I want to figure out the power series representation for ln of 3 minus x. Here I'm going to have to choose x less than 3. It's going to be restricted more than that, but at the very least it should be less than 3 for the natural log to exist. and we notice that this is in fact minus the integral of 1 over 3 minus x. Right, so the integral of 1 over 3 minus x is minus ln of 3 minus x, and with the other minus it becomes positive. And if I manipulate the terms, I can apply the geometric formula for the stuff under the integral. So I can move the 3 out. So pull the 3 out on the denominator. So that's 1 minus x over 3. And let's see, we can take 1 over 3 out of the integral. And now inside the integral, we can apply the formula. So inside the integral, I can replace that function with the summation from 0 to infinity, x over 3 to the power n dx. Now at this point, notice that x over 3 should be between minus 1 and 1 for that to converge, which means x should be between minus 3 and 3. Or to be more precise, in our case, is actually 0, 3. No, sorry, minus 3 and 3, because x could be negative. Yeah, that's fine. So just between minus 3 and 3. As long as it's less than 3, the natural log exists, is defined, right? So we're not done, right? We still have to integrate. But from what we mentioned before, we know we can integrate inside the integral. We can integrate inside the summation. Actually, let's do one more intermediate step. Let's remove 1 over 3 to the n separated from x. So it's going to be 1 over 3 to the n x to the n dx. And now we can integrate inside the summation. So 1 over 3 to the n is a constant with respect to x, and now integrate x, which is x to the n, which is x to the n plus 1 over n plus 1. Finally, you can bring inside minus 1 over 3 or plus the constancy. I forgot the constancy from the integral. So it's going to be just the constant of integration minus the summation from 0 to infinity, 1 over 3 to the n plus 1 with the 3 from outside the summation, x to the n plus 1 over n plus 1. All right, now pay attention here, this constant must be determined. So right now we concluded that ln of 3 minus x is the summation from 0 to infinity, 1 over 3 to the n plus 1, x to the n plus 1 over n plus 1. To determine c, you can plug in any number for x you want, and then determine c. So plug in any number for x, but the best one will be x equals 0. You can plug in any number for x, but the obvious one which quickly gives you the value of the constant c is x equals 0, because that cancels the whole summation. If I replace x with 0, that summation is 0. And then you can quickly find c to be ln of 3. If you plug in any number besides 0, you're going to have c itself in terms of a convergent series. That won't be a mistake, but it's really far too tedious than it's necessary. So in bottom line, the representation of ln of 3 minus x is natural log of 3, your constant, minus the summation from 0 to infinity, 1 over 3 to the n plus 1, x to the n plus 1 over n plus 1. All right, so we're going to do another example, and that'll be probably the last one on the next page. And always remember that the strategy is really the same in all of these problems. It's just algebra manipulation to eventually use this formula. With the additional thing that in this case you may integrate or differentiate inside that summation if the representation contains that derivative or integral. So let's move on to the last page, hopefully. All right, so let's finish the lesson with an example that really illustrates the usefulness of this concept of power series representation. So suppose you want to approximate the following integral to 6 decimal places. Let's say the integral is from 0 to 0.3 of x squared over 1 plus x fourth dx. All right, so I noticed already, well, it's not that quick notice, but based on the examples we did so far, hopefully you guys will notice already that this quantity x squared over 1 plus x fourth, it's actually can be written in terms of, can be written so that I can use that formula, 1 over 1 minus x equals summation of x to the n. So I'm going to put this here in a rectangle so I can use it. But then let's do that and integrate and see how we actually could answer this question, you know, like how do we approximate the integral within 2 decimals. I want to point out that otherwise this integral won't be easy to solve. I don't even know if it's possible, but in any case, it's not a trivial integral. You should notice that the u substitution for the bottom term doesn't really work because du will be in terms of x to the 3, and on the top you have x squared. I don't know if trigonometric substitutions will work, but anyway, it's a pretty difficult integral to deal with. But let's say our goal is just to approximate it. Then we know we can replace this with a power series. And presumably, if we use just a couple of first terms in that series, maybe that's good enough to approximate the value of the integral. So without needing to have fancy methods of integration. So first, let's actually do the manipulation so we can apply this formula. Inside the integral, so we're going to keep x squared out. And we're going to write that plus as a double negative. And now that allows me to replace 1 over 1 minus negative x fourth with summation from 0 to infinity minus x to the power 4 to the n dx. We're not ready to integrate yet, right? We're still manipulating this. And then, so we need to write it as a power series, and then we can integrate inside the summation. So we're gonna remove, take out minus 1 to the n, and then x to the 4n. Now bring x squared inside the summation. Now we have the inside of the integral as a power series. And now it's time to integrate. So we have summation from 0 to infinity. We integrate inside the summation. Power rule, x to the power 4n plus 2 plus 1, that's 4n plus 3, over 4n plus 3 between 0 and 0.3. So you're going to do the fundamental theorem of calculus just like you do with any integral, except you plug in those numbers inside that summation. So 0.3 to the 4n plus 3. And the other piece is 0, but let's just write it so it's clear where it comes from. When I plug in 0, obviously this is going to be 0. So we concluded that my integral of my original function is in fact equal to a series, a power series. Point 3, excuse me, 4n plus 3. So in many branches of mathematics, in fact, if you have the answer in terms of a numeric series, that's very good. I mean, it's in a sense, this is a number like as good as any other number, because you know this is convergent. Now, you may not know what that is equal to. It may not be possible to find the exact number, but it's still an exact answer in the sense that we know this is a convergent series, so that is the answer. It's just that we don't have an answer in terms of a traditional number, real number. But nevertheless, even if you have it in terms of a series, we can at least approximate it. Now notice this is an alternating series. And remember, we learned that in an alternating series, the n+1 term, disregarding the minus, gives you the error of computation if you add the previous n terms. So to be more precise, let's actually write down the first terms in that summation. So when n equals 0, we have -1 to the 0, which is 1, 0.3 to the power 3 over 3. Then when n is 1 is minus 0.3 to the power 7 over 7. Then the next one is with plus 0.3 to the power 11, 8 plus 3 over 11, and so on. So if you use the calculator, notice 0.3 to the 11 over 11 is actually 0.006016. So this is the error of adding the previous terms. So the previous two terms. So that's the error between the exact value and adding the first three terms, the first two terms. So you are already within 6 decimals, right? So the fact that the third term has 6 zeros after the decimals means that just adding the first two terms is enough to be within 6 decimal places. So if you do the computation here for the first two terms, you get 0.008969. So that is the approximate answer, the approximate integral. All right, so I hope you're convinced that this is indeed useful. What happens in the last lesson, which will be a little bit longer because it's important to understand the concept before we move on to actual examples. We're going to obtain power series for not just for functions reducible to 1 over 1 minus x, because not all functions are reducible to this. For example, what if I want cosine of x as a power series? You can't use this formula 1 over 1 minus x. And we will learn that not only we could do that in general for functions that are indefinitely differentiable, so functions that can be differentiated at various points an undetermined number of times. So not only that's possible, but the center of that series, notice so far we had series centered at 0, right? Remember, in general, a power series looks like this. But we will see that the center you pick, because you can pick it most of the time, matters in terms of how easy it is to approximate the original function with a power series. Usually, the center of a series should be chosen as close as possible to the range for x that you want to approximate, basically. So if you want to approximate, for example, functions for values 1.1, 1.2, 1.3, and so on, then it makes sense to have a power series centered at 1. So that leads to the concept of the so-called Taylor series, which are power series used to represent functions that I mentioned. So that's it for today. We'll see you next time.